Great, well, we'll get going. Hello, everyone, and welcome to this Gene Golding Institute Bristol Data Week 2023 session on deep learning with TensorFlow for skin cancer classification. And today your hosts are James Pope, Effie and Zara, who are also sharing the video with me now. A quick introduction to Bristol Data Week. This is a week of events, both online and in person this week, run by the Gene Golding Institute at the University of Bristol. A little bit of housekeeping before we start the session today. There is a code of conduct for all of our events, and my colleague Will, who's from the JGI as well, will be sharing the link to that in the chat now for those of you joining us. We're currently recording as well, so that you'll be able to watch back any parts of the session later on. So if you're not happy with your video being recorded, then you could feel free to turn that off. On that note, please can you keep your microphone muted unless you're asking a question. We've got the chat, which again would be a great place to ask questions during the session, and actually a great chance now to introduce yourself to everyone and to the speakers here. So please feel free just to introduce yourself to the chat now, say who you are, where you're from. And then the eagle-eyed of you may notice that we have some breakout rooms as well, which we'll be using in case anyone has any kind of technical difficulties or queries later on in the session. You'll be able to drop off into one of the separate rooms, and then one of the speakers or assistants will be able to help you and then come back into the main room as well. I'm just going to give you a very quick introduction to what the Gene Golding Institute is. We are one of the 5 university research institutes at the University of Bristol, and we are named after Gene Golding, who is a researcher at the University of Bristol, who created and founded the Children of the 90s study, or the ALSPAC study, which you may have heard of, which is a study that's tracked children and their families over since the 1990s onwards, and has collected lots and lots of data on them, and has become a huge resource for medical research. Jean still works at the university, and it's kind of an honor that our institute is named after her. And we're also the link to the National Data Science Institute, which is called the Alan Turing Institute. Just to give you a quick run through of some of our events this week, there's an online calendar of all the events that are taking place this week, and Will is going to pop the link to that in the chat as well. So we're currently on Tuesday, but we've got more events in person and online, training and talks and seminars Wednesday, Thursday, Friday, and we'd really encourage you to come to an event that we're holding on Thursday at the Bristol Beacon, which is running 10 till 5 all day, and there are a number of talks and workshops and also exhibits that you can come and have a look at. Just a quick thank you to acknowledge the support of our sponsors, and this event wouldn't be possible without them, so thank you very much. And then finally, if you are using social media, please feel free to share this event and share your experiences using the hashtag Bristol Data Week. You can follow us on Twitter using the handle @JGI Bristol, and there's also loads of other ways of staying involved and in touch with us. We've got an online data ethics club, data visualization interest group, and the way of finding out really about all of our events is to subscribe to our mailing list. So our website at the bottom right there, bristol.ac.uk/Golding, will get you more information on that. Thanks, Will, for putting everything in the chat. And that's enough from me, and I'll hand over to our hosts for this session.
Thanks, James. So hopefully everybody can hear me. And let's go get this. And hopefully everybody can see the slide. Excellent. Okay. Welcome to our session today. So my name is James Pope, and we'll be presenting this along with Effie and Zara. We're all lecturers in the data science, the data science program at the University of Bristol. A little marketing also from our side. As I said, we're associated with the data science program, which includes a PhD and a master's in data science. Also, we have a distance learning program as well associated with that. And we're also associated with the digital health program, which also uses obviously data science techniques, and specifically for this session today, we'll actually look at looking at skin cancer images and classifying them. So this is in some sense inspired by that program as well, and they also have a PhD and MSc. This material, to be clear, has been assembled from different sources. There is the book Hands-on Machine Learning. So some of this material is borrowed from this. There's a GitHub, which has some of the code. We've modified some of it, and also from Andrew Ng's Coursera course. The skin cancer example, however, is an example that we've put together here at the University of Bristol. The tentative schedule, we're going to go through the first part of this. We'll go through some slides as I am now, and we'll have a lab. So we expect that you already have Colab, or at least Google set up to set up Colab, Google Colab. And we'll do that first to make sure everybody has that set up. So we'll go through the slides as we are now, do that lab. Then we'll go through part one, which is a little more of TensorFlow. We won't jump straight into CNNs and skin cancer images. We'll make sure that some basics are taken care of in part one. Again, that will consist of some slides and then a lab, followed by part two, which is where we will actually get into cover CNNs, the different techniques, and then actually look at skin cancer images. So this is an overview of these learning objectives for today. To give you an introduction to CNNs and an awareness of how they could be used to classify skin cancer images, and also to think about the performance and particularly thinking about transfer learning. So we'll take a look at an example of that as well. So those are the learning objectives. As I mentioned, some level background expected that you have done some work with Jupyter Notebooks. We'll do all of the coding in this. The labs will be done using notebooks, specifically running in Google Colab. And so also, it would be good if you had some introduction to CNNs, but we will go over some of the basics. We won't be able to teach you, be an advanced CNN expert in this session, but we at least will be able to at least get you to where you can appreciate how to use them. This again goes through it, that reiterates the fact that we'll give examples of this, and certainly hopefully a stepping off point for you to go on and explore these CNN techniques for your own problems, or maybe you want to continue looking at skin cancer, but certainly we will not be able to go, like I said, dive into all the details. So with that, with this first scary looking slide, hopefully not too scary looking, and I guess, did you guys see me drawing here? Do you see this drawing here? The scribbling? No? Okay. So the little pointer tool, so I'll just maybe move my mouse. Maybe you can see that.
Sorry,
Go ahead.
James. I think if you look on Zoom, there is an annotate button. I don't know if you can use that.
Yeah. So let's try. Do you see that?
Yeah. Yes.
Okay. Now, how do I get rid of that? Erase all. Let's see. Erase. Okay. Okay. So on the left-hand side of this, what you see is this black box, this dotted black box. You can imagine that it's basically, you can treat it as a black box, that on the left you have the input, just like a function, and then you have the output of the function on the right-hand side. And there really, it takes the inputs and multiplies them with these weights just in a linear fashion. And then it adds a bias to it, and then sends that through a nonlinear activation function. I realize there's a lot of terminology in that, but if some of this confuses you or worries you, I think one way to think about this is that it represents a function that you're taking the input and you're going to map it to some output. And many times this is either going to be either classification. In other words, the function is going to learn how to map the input, for example, the image, to 7 different types of images, or mole types, I should say, not types of images, to 7 different mole types. That would be a function. The function could also be a regression, which is to take the input and then to predict a number. And so this is really what this is representing within this black box. And when we say that we have an algorithm that learns, how can one say that learns from the data? What we really mean is that you're learning those weights. One thing, the input is something you have. You have the image or you have the information about a person, for example. And what you want to do, you have that, and you want an output to predict an output. But what you don't have are those weights or the bias. And so when we say you want to learn from the data, what we mean is you want to learn the weights and biases for this function. And that's what the perceptron is doing. This is fairly simple. As you can see, this is in some sense one neuron. So the little blue circle is representing a neuron that takes these inputs. And again, it has its own set of weights, a bias, and the activation functions. And this is all within a layer. You can see this is kind of on the outside there. And really some questions to think about as we move forward are, can you have more neurons? What does that look like? And you might have more neurons within the layer. What if you have multiple layers? What do multiple layers mean? And we'll cover some of this. And also, you might think about the activation functions and what they might do, and we'll discuss a little bit of that also. So these are all the things that you need to think about, and this is a very simple approach or start to thinking about these things. And so hopefully, yep, so I may have froze there for a second, but hopefully this makes sense that, or at least hopefully you're getting a little understanding and not that this is really what this thing is doing. We're trying to learn the weights and biases of this. Okay, so what can we do with this? Well, this is a classification problem where this is a very typical example where we're given the petal width and the petal length for a flower. And what we want to learn is a decision boundary between the two, so that if the petal width is very large and the petal length is very large, what we want it to do is to predict in the blue area in the upper right, for example. And then, of course, if the petal length and the petal width are small, we would end up classifying this as yellow, or I believe it's iris or not iris. This is a binary classifier. So, and that's what this one would be learning. So this actually comes from, if you look at the code on line 3, you can see that this is actually scikit-learn. This is not TensorFlow. But scikit-learn has a perceptron, and so it's a very simple type of artificial neural network. And so when we create it, so it's got the inputs. So the inputs in this case are going to be 2, the petal width and the petal length. And the output is going to be whether it's an iris or not iris. That's what it's going to predict. And so what you have here when you're looking at the code here on line 7, this is the input, and line 8, this is actually the annotated, the real answer, so to speak. This is what we're going to use to train it. On line 10, excuse me, we create the perceptron. On line 11, we fit it. And we learn what's happening on line 11 is that from the data from X, the input data, and what we know the answer is Y, the labels, it will actually learn the weight and bias for that perceptron, or for that function, if you like. And then from that, now that you've got it, you can use that to make predictions. And in this case, it's trying to make a prediction that if you have, I believe this is petal length of 2 and petal width of 0.5, it'll make a prediction of that. Okay, so that's an example of using it. And I guess at this, and I should say the perceptron uses a special type of activation function. And really this starts to motivate, how can one say, what about different activation functions? Like I said, what about multiple neurons? What about multiple layers? And really what we're motivating is that the perceptron and what scikit-learn is providing us here is not sufficient to do what we want to do, because we do want to look at more sophisticated architectures. So this is an example of one that is more sophisticated. As you can see, now we have 2 inputs like the iris example that we just gave. And now what we want is to have 2 layers. The first layer is going to have 4 neurons, and the second layer is going to have 3 neurons. And this is a classification example where we're trying to classify from 3 different things, 3 different classes, if you like. And now in this one, the first layer might have a different activation function. We represent that with G. I'll talk about a couple of different types of activation functions. And so in any case, the point here is that now we have multiple layers. And as we'll see, this idea of multiple layers is quite interesting. The interpretation is quite interesting. I think, again, a very high picture understanding of this is to say on the left, we have the input. Everything in the middle is, if you will, in some sense, a black box again. And then on the right-hand side, we have the output. So again, it's learning a function, but this function that it's learning is actually much more sophisticated. Now, it's actually able to learn much more sophisticated functions because we have these multiple neurons. And actually, the multiple layers come into where it can actually start to take combinations of features. We'll talk about feature learning in a little bit. But in any case, the point of this is to say that we would like to create something like this, and scikit-learn doesn't let us do that. We need a nice framework that allows us to create these layers with multiple neurons and different types of activation functions. So with that, before I jump into, I guess, the TensorFlow, I think we may cover that in the next slide. The different types of activation functions, it's very unlikely that you will need the heavy side function, which is what the perceptron used. The ones we typically use are ReLU, sigmoid, and tanh. When you don't know, usually ReLU is what you use. If you have binary classification, use the sigmoid for the output layer. And if you have let's see, if you have a multi-class classification problem, multi-label classification problem, if I've got that terminology right, you would use the softmax. We'll go over some of these, so don't, if you don't remember it now, don't worry about it. These are provided for us. I think really, the main parts of this, that these are fairly well known from research about which ones you should use when. And again, the default rule is if you don't know for those hidden layers, the default rule now is to use the ReLU. Okay? So, like I said, why do we need TensorFlow? We want to have multiple neurons within a layer. We want to have multiple layers. We want to have different activation functions and potentially different loss functions. And TensorFlow allows us to do that. You may say, well, what about PyTorch? Well, PyTorch lets you do that also. Okay, so PyTorch and TensorFlow are basically deep learning frameworks. I have no position on whether one is better than the other. I think they're both quite nice. And so we use TensorFlow, but I would say that there's no reason why you shouldn't, if you want to use PyTorch as well. I think some of the other ones have in some sense gone away. I think the two primary ones to focus on right now are really TensorFlow and PyTorch. A little bit of background about PyTorch. It was developed by Google, and they provide, it's actually written in C++. However, it also has APIs for many different types of languages, and we will focus in this session on Python, and we will be using the Keras API to it. The Keras API was meant to be a little more broadly, support many different types of libraries. Sadly, it doesn't support PyTorch, but so in any case, basically at this point, when you use Keras, pretty much everybody assumes you're using TensorFlow. Okay. So a little more about the architecture, but we really don't need this so much. But like I said, we will be using Python in this session, and we'll be using the high-level API. We're going to use Colab for the session today. If you wanted to go set this up in your own Jupyter notebook, here's kind of the requirements file for setting up all the dependencies. But like I said, we will end up using Colab today. And so this should be available to you. This link, this is the GitHub repository. It has the presentations that I'm giving to you now, and also the notebooks that we're going to use. So with that, and I believe that is, it says follow instructions to run the notebooks in Google Colab. And with that, I will stop, because what we want to do now is to start the lab and to make sure everybody has Google Colab set up, and that we can go and start, start running code. So are there any questions before we jump off to that? Or any comments? I don't know if there were any comments in the chat while I was waiting. Okay, I think I will turn it over. I don't know, Effie, if you wanted to start on the Colab part.
Yeah, sure. Hi, everybody. So you should have the link to the GitHub repository in the chat. So let me share my screen as well. So hopefully you can see the GitHub repository right now. So if you click on that link, it should take you to this repository. And you will be using this through Google Colab. So if you have this link up and then also open Google Colab, so if you just type Google Colab, it should take you there, and it should immediately give you this pop-up. So what you need to do is click on GitHub here. That does it immediately for me because I just connected it, but you should be able to just put the GitHub URL repository that is in the chat here, and it should be able to basically show you. Okay, let me get, I have the Zoom bar in front of my, how do I take this away? Okay, found it. So if you take this URL link and paste it back to Open Notebook, click on GitHub, put this link here, it should be able to show the 2 notebooks that are on that repository. And then we will start with part 1. And then at some point, we will tell you when we may move to part 2, but you will follow basically the same procedure. So if you click on part 1, it should take you to this page, which is the notebook. And again, you have some sections in the beginning about the material that we have been using, and the content and the code that we will be running. So I would also suggest before you start to click on runtime and change runtime type and try to select a GPU accelerator. You might not necessarily get one. It's a bit random unless you have paid for Colab resources, but it's good to try it and we'll see how it goes. Essentially for this notebook, it should be okay whether you have a GPU or not. The difference will be in what data sets we will use in part 2, but we will come to that later. So hopefully everyone is there already. Anyone has any problems up till now? Okay, I will take that as a no, and everything is fine.
So maybe we'll have a thumbs up if you manage to get this up and running. So it's we need a couple of more minutes for people to put this through. And once you get through this and we get Colab up and running, if you can just make thumbs up in the chat or somewhere, that would be great.
I see several have got it working in the chat, which is very promising.
Yeah. Okay, so on the left-hand side, in case this is closed, you can open it by clicking here and you can see the table of contents. So you can see that we have already discussed the perceptron, scikit-learn. So you scroll down, you can run each section by clicking on the run button. If you see this, it's fine. You can click run anyway. So every time you run each section, it might take a while. I don't know why this is taking so much time for me. Okay, we got there. So basically in that way, you can run each of the sections and see the output right below it. And you can run up until the perceptron that we discussed. And we have some discussion points here. So if you can run up until this point before we move on to TensorFlow, so that we can at least make sure that everything works up till now. So yeah, we will wait for a few minutes until everyone has run it.
So I see lots of
you're
thumbs
on
up
mute.
and thumbs up. So hopefully everybody's. We'll give a few. I guess wait a little bit more. And I don't know, Effie, if maybe we go through and discuss these questions, or see if students might. I say students. Excuse me, participants may want to answer some of these. But maybe we could take a stab at some of these questions about that we're looking at now.
Yeah, that's the idea. I mean, was hoping we have some participation from our audience. So if anyone wants to try and address any of these points, would be great. You can, if you don't feel comfortable unmuting, you can write in the chat, or feel free to raise a hand or unmute yourself. And say.
I'll give a hint on the first one. I did say the perceptron used that heaviside activation function. So maybe there might be a difference there with logistic regression, maybe.
So the similarity would be mainly the linear kind of boundaries between, if you're familiar with how logistic regression works. So this looks very similar to the boundaries in logistic regression, but the way it works is different. So maybe some of the later questions, if anyone has an idea or wants to share.
We have a hand from Jay.
I was going to ask, can you hear me? Okay, cool. First, so I missed what you said on the first question. So is it effectively similar to logistic regression? However, this particular heaviside step function you're looking at is the output from the logistic regression more than a half or less than a half. So you're kind of saying what's the most likely or most probable class?
Yeah, that's
what you're outputting here.
Yeah, the perceptron, at least in this one, is a hard decision boundary, and that's what that step side function does. It basically makes a hard decision that you're either iris or not iris, or excuse me, iris setosa, not iris setosa, binary classifier. And so that the perceptron, when you say it, implicitly the activation function is that hard decision boundary. The logistic regression actually has a sigmoid activation function, so it's going to give you a number between 0 and 1. And it actually starts to give you a more kind of like you said, the likelihood of it being that class. So that's the primary difference. And I think that at least when I first started to learn neural networks, artificial neural networks, I had to take a step back and go back and learn that this is really the building block. The logistic regression is really the building block of each neuron, and it does give you that kind of self-classifier, so to speak, approach to it. And that, to me, that's the primary difference between the perceptron and logistic regression. And so your answer is exactly right, James. So hopefully what I said also supports that or makes sense.
So if you'd used the logistic regression and the sigmoid activation instead, would you expect these two colors to have like a blurry edge, as it would change from one to the other more slowly?
Exactly. And in fact, when we go through later, actually, and when we look at the TensorFlow, we'll repeat this, except we'll actually provide exactly that. And actually, then what will happen is you'll see the more of kind of a gradient going from one class to the other.
Cool. Thank you.
And I think I don't think for the I think that's the main difference, really, the activation function, that soft classifier versus hard classifier. The multiple units and multiple layers, a little harder to answer that one. But I think for everybody listening, all the participants, this is certainly an important question to think about. We will get closer to answering some of this later, but you could imagine that each unit is a function, is learning something different, so to speak. And when you get different layers, you can have the later layers take what the earlier layers learned. And so in some sense, you can think that those earlier layers, each of those neurons are units, is actually learning some useful feature, so to speak. And so this is where this idea of feature learning comes from, but we'll give a little better answer of that one coming up. And I think about the different activation functions. Like I said, sigmoid is very good for binary classification because it gives you this soft decision, so to speak, or the likelihood of it being one of the two classes. So that's important, an important difference on the activation functions. When you get to multi-class classification beyond binary class, we use the softmax, which again does something very similar. And finally, we didn't talk much about it, so I'll go ahead and somewhat we can certainly think of the loss function. The loss function is different depending on the problem. For classification problems, it's usually entropy. It's called the cross entropy. This is provided for you, so you don't have to go do it. And then regression, you usually use something like mean squared error or the mean absolute error, for example. And the loss function, when you're learning, you're basically trying to make it lower. So it's really an optimization problem. When you're learning is you're trying to minimize this loss function. And this is what's happening when you see the epochs go by. It's basically minimizing that. And again, different loss functions for different types of problems. And that's how these things are set up now. And so I should say you could look at regular linear regression. And many of the same things are there. I don't think they have multiple units, multiple layers, but they certainly have a loss function and it's mean squared error. So in some sense, the approach that we're taking here with artificial neural networks expand the idea of linear regression to be able to solve classification problems and learn much more complex functions. So if you do know about linear regression, you say, hey, I've already done this where we train it and we minimize the loss function. This is true. We typically use, there's a way to minimize the loss function in linear regression with a closed form linear algebra. But many of the problems, once you get beyond that, it actually becomes very difficult. There's not one global minimum, so to speak. And so in any case, we use the gradient descent algorithm to actually minimize the loss function. If all of this is a bit over, I know we're not going into depth on it. I just want to kind of basically summarize that when you're training, what the TensorFlow and other deep learning frameworks are trying to do, they're trying to minimize that loss function by changing the weights. So a little bit more information about what's happening when training is going on. So yeah, that's it. So that's sorry to answer the question, Effie, but I'll turn it back over to you. And let me know when you want me to start on part one.
Yeah, thanks, James. No, go ahead, please. I think it's time to go to TensorFlow.
We've just got a question in the chat from Matt saying, is it true that if the objects you were trying to classify have multiple distinct features that can be used to classify the images, that you would need more layers within the network?
I would say so, yes. That generally the earlier layers, and this is the part that gets a little how can one say, becomes much harder to interpret for humans. For what the participant said is exactly right, that the more features you want to learn, how can one say that you normally need to stack more layers. And so that's exactly right. How many you need, that's debatable. And that's a little harder to, like I said, when you start to look, and we'll see one today that's 50 layers deep, I can't tell you that the first 10 layers are learning these features and the next, 20 layers are learning these features. That becomes very difficult to interpret. But in general, that is correct.
Yeah, Matt says thanks.
Yeah, great question.
Okay, so I will stop sharing and then get over to you, James.
Okay, let's see if I've got this. Hopefully I can get this. Again, hopefully everybody can see my screen. Okay, so to continue, this is the exact same code. The exact same architecture that we ran with a slight difference. We're now using TensorFlow, and we're using a different activation function. So as James Thomas was saying, it's the same problem that you can still see we have petal width and petal length, and we're trying to learn the decision boundary between the two of them. So as we walk through the code, if you look on line, everything is roughly the same. We have different imports for TensorFlow, but line 11 is very important because we have one dense layer with one neuron. So that basically just creates the one neuron, the one unit. I should say units equals 1 is what creates that. And the activation function, instead of being the Heaviside step function, is now the sigmoid. So that's going to give us a number between 0 and 1. And then we put that in a layer. We stick that into a sequential layer. And that becomes the model. I've used terms there just a little bit. Line 11 creates the layer, and then the model is on line 12, and it's a sequential model. So it's a sequential model that has one layer. And so this is very similar to what we saw previously with scikit-learn. We now compile it. We didn't do that with the other one. I think we just did fit. With this one, we have to compile it. We have to say what the optimizer is. That's stochastic gradient descent. That's the algorithm we use. And what we want to do is to minimize the loss function, which in this case is the binary cross entropy. Finally, line 14 is where it actually takes the data, the input data and the output that we expect. And that's what trains it. That's what learns all the weights and biases. And finally, we can then use that model to make predictions. And now you can see, instead of making a hard decision, you can see that it's kind of a gradient. You will also note I have two different versions here because actually the way that this version works, stochastic gradient descent, I should say that it starts with, we basically randomly start with the weights. So every time you run it, you might get a different boundary. This is sometimes not wanted, but it's something you should be aware of, that depending on if you're randomly initializing the weights, you may find a different boundary, okay? So absolutely what we'd seen before. And so now we've made a big jump because now we can actually think about creating much more sophisticated functions. And that means more units in a layer and more layers. Okay. As an aside in a sense that today we're primarily concerned about getting to classification CNNs for skin cancer data, but you can use this for regression as well. There's not really a huge difference. The difference usually is within the output layer and the activation function for the output layer. So here we have the data we have is on line 4, the X's and the Y's. I think that's a fairly simple function. You can look at it a while. You can probably learn yourself what that function is. We call that human learning. In any case, the machine would like to learn this as well. So in this case, you can see that it doesn't actually mention the activation function. And if you don't mention it, the default is linear. So this is actually going to be a regression problem. It's got one unit, so it's going to take the input and try to learn the weights to produce the output, which is on line 5. And I think for this example, if you input 10, I think it's times 2 minus 1, if somebody corrects me if I'm wrong, that if you take on line 4, multiply the input by 2, and then subtract 1, that's the function. That's the function we want to learn. Again, you don't need machine learning to learn this function, but it's satisfying that the machine does get close to this. And so if we put a 10 in, the answer we would expect would be, was it 19? And so we run it. Notice we also have the epochs, the number of epochs. This is how many times we go through and try to adjust the weights to reduce the loss function. Generally, the more you run it, the lower the training loss will be. And we'll talk about this in just a moment. So a little bit of other terminology, again, just to start to get into this more. Some participants will already know this. What we want to do is to take our data and split it up into, because the training data, we can always, in some sense, arbitrarily get the loss to be as low as we like. And that's really called overfitting. What we want it to do is to be able to predict well on data that the model hasn't seen. And so what we do is we keep a test set to basically help us kind of as a proxy for data we haven't seen yet, so that we can generalize our model. Okay, so typically what you do is you might take a 60-40 split or something like this, and you just randomly do this. So again, not are typically the weights are random, but many times when you actually take a new training test split, you also will usually randomly select those also. Okay, so finally getting on to images a little bit. So now we're like, okay, now let's think about if you give me an image like this on the left, this is the fashion MNIST, and I think there are 100 or million of these, I can't remember, and they've all been classified, and there are actually 10 different class types. How can we use our new knowledge to actually predict this, the class type from these 10 images? This is an ankle boot, I think is the name of this thing on the left, the type. And so that's the input and the output on the right. We hope it to be one of these. This is going to give us a, if you will, the probability or the likelihood that it's of that type. So as you can see, and this example is 5% that it thinks it's a t-shirt, 5% trouser, etc., 10% sandal, and the highest one there, as you can see, it's a little confused. It thinks it could be a sneaker, 25%, but 30% ankle boot. And so you could imagine the reason it does that, by the way, we get those probabilities is the activation function on that last layer is a softmax. And that's what you use when you have when you have multiple classes that you want to try to predict. Typically what you do in this case is you take the max and you select that as the class that was predicted. Okay, so this one has two, if you will, hidden layers. What's interesting is the first layer here doesn't learn any weights. It's just taking the image and making it just, the image is two-dimensional, if you will, rows and columns. It just makes it one kind of column, if you will, just one row, if you will, or one column. And that's the input. Now you can imagine that, okay, 784 pixel color values, this grayscale. This is a little problematic because you could imagine that once we flattened it like this, maybe the spatial representation, the two-dimensional representation meant something, right? When we look at humans, when we look at an image, we're thinking of kind of an area within the image when we're trying to classify it. And right now, by flattening it, we've kind of lost that spatial, the neighbor, if you will, information. So this isn't great. So this representation isn't great, but nevertheless, we can do this. We flatten it. Then the two layers there, the dense layer, we have two of them. Again, the first layer may learn some basic features. The second layer may use those features to learn higher level features. And then we finally make the prediction in the output layer. And this code, let's see, there we go. And so with this code, this is again, not a CNN. We'll look at something a little much better than this. But this is what that code looks like. Okay, this is what it would look like. And this one does okay. I can't remember what accuracy we get on this one. It's actually not too bad. But let me see if there's anything different in this code. One thing you'll notice is we have the input layer on line 3. That's just a flatten. Excuse me, that's the input layer, and then we flatten it on line 4. You can see that the two layers, those two dense layers, that the first one had 300 units. The second one has 100 units. And then on line 7, that's the output layer, we have 10 units. So if you're doing a multi-classification problem like this and there are 10 classes you want to predict from on line 7, that's where the 10 comes from, okay? We'll see for skin cancer, we have 7. There's 7 different mold types that we want to predict. And again, since this is a multi-classification, we use the softmax activation function in the output layer, which is on line 7. And on line 5 and 6, when in doubt, use ReLU. Okay, so this turns out to be fairly good. Again, these are some of the things that hyperparameters that you may adjust when you're trying to tune the model. But for this session, we're generally going to choose ReLU as the for the hidden layers, and then softmax for the final output layer. Okay, you can see at the bottom, it gives you information about how many weights that are being learned in each layer. And you can see in this case, it's learning 266,000 weights. So quite a number of weights. We would not want to do that by hand. And so pushing ahead fairly quickly, the layers we've been setting up are very sequential. One layer feeds the next layer. And so we can do this with regression as well. So this is an example of using a regression model. And in this case, again, just very quickly going through the code, if you look on line 14, 15, 16, and 17, that's actually very much the representation that we had just seen. We had 3 hidden layers, those dense layers, and then the output layer. The output layer has one unit. And again, if you don't say the activation function, it's assumed to be linear. And this indicates that we want to do a regression problem. We again trained this for 20 epochs, and there's some other code down to evaluate it, etc. One other thing that I had alluded to on line 5, we took this data. This is actually a housing data, so we want to predict the price of a house. And you can see that we took all of the data in as it was on line 4, but then on line 5 we split it into the train and test sets. Okay, and so hopefully it's clear that on line, let's see, 21, we're learning those weights using the training data. So you can see X train and Y train are in there. And then when we evaluate the model on line 25, we're using the test set. So you can see that the X test and Y test are there. Okay. So some other things, you can actually get more sophisticated with this. How can one say you can use the functional API, which gives you some more flexibility in creating the architectures that you want. For this session, we're generally going to stick to the sequential architecture, but if you wanted to create other types of architectures, the functional API is the way to do it. And so at the top here, lines 1 through 6, this is using a sequential model. If you wanted to use the functional API to create an equivalent one, you'll see on the bottom there, the lines 1 through 14 do the same thing. What happens is you create each of the layers individually, and then you explicitly pass in to each layer the input and get the output. And then you take that output and pass it into the next layer. It's a little hidden in the first part of it that's done for you. You don't see that it's taking the input from the previous layer. That's kind of nice that it does that for you, but you should realize that really what's happening is the output from one layer is being fed as input to the next layer, and the functional API makes that very clear that that's what's happening, okay? But it also allows you to do things like this. The functional API lets you create things where maybe the output from a layer doesn't go immediately to the next layer. Maybe you skip ahead to a layer much farther down the line, much farther in the architecture. And so this is used commonly. So when we start to look at the different types of ResNet and things like that, they typically will create more sophisticated architectures like this. This is a very typical one called a class of an architectural class, if you will, which is a wide and deep neural network, where you have this kind of more short path going through the top there, and then this long path that goes through all of the layers, as you can see, the intermediate dense layers. And so the way you would create this would be to use this kind of the functional API. And here's the code that, if you look at this architecture, the code to create that is here. This is, let's see, this is looks to be a regression problem. So you can see that the output layer, let's see, everything hopefully is correct here. But what's telling me that is the loss function is the mean squared error. You can see the optimizer, instead of stochastic gradient descent, we've changed that to atom. That's a typical one that you should use today. It turns out to be a little better than SGD. And then let's see, we trained it for 10 epochs. So in any case, that's an example of using it, but we could also use this in regression as well. Okay, so very quickly, I'll go through these and we'll jump back into code, get into the lab and start to see some stuff going instead of you listening to me talk. Normally when you call fit, you might wonder, what is it doing? I said it's learning those weights, right? You're basically taking the training data and the answer you expect, the Y train, and you want to learn the weight. So every epoch you go through, you'll see on line 3, that goes through one epoch. So it's going to basically take a batch, go through all the batches, and basically adjust. Basically does this backward propagation, adjusting if you will, learning the gradients, and then adjusting the weights. The way to think about this is it's moving the weights in a way that reduces the loss function. And it removes it a little bit each time. So every time you go through the epoch, you expect to continually move closer, reduce the loss function each time you go through this. And so that's a little bit of what's happening. You could write your own training loop. Some people do. In this session, we'll be happy just to call the built-in training function. And again, a little more information that the forward pass just basically goes through and gets the prediction. You can compute the loss from that using the loss function. And then the backward pass takes that and then adjusts the weights and biases. W and B, as you can see there, is what's actually happening. And that happens in every epoch. And here's what it looks like when you run it, multiple epochs. So what's happening on the x-axis is we've run this for many epochs. We can see the red line at the top here. That is the accuracy on the training set. And then the dotted red line is the loss function on the training set. Sorry, I did not put train in there. Apologies. But the red line is on the training data. We care about the training data loss, but what we really care about, what you should care about, obviously, is how does this generalize? How does it look on the test set? We're using the validation one as, if you will, for the test. Subtle differences, but we'll use the validation loss and validation accuracy for the real answer of how well the model's doing. And as you can see, the validation accuracy is getting up in this case, in this example, got up to around 90%, but you start to see a gap. And you see that not only the loss function, you can also see, look at the loss and start to see they diverge. So we can see the training and the test or validation loss start to diverge around 10 epochs. And perhaps around 40 epochs, we really see a divergence between the accuracy start to diverge. This means you're overfitting. Okay, so this is certainly one of the ways that we can detect this. There are ways of doing this. I think we've got the API. Yeah, I think I will talk about the callback. But in any case, once we've gotten a good model, hopefully that's not overfit the data. We want to save it. So there's some code to save the model. So this is very important. Another nice thing to have in your toolbox is basically a way to try to stop before you overfit. This is still a research area, but this is a fairly nice built-in one called early stopping. And so we do have the code for this. When we do the CNNs later for skin cancer, we don't use it, but you should absolutely be aware of this. And what this one does is when you start to see the loss or the accuracy diverge, it stops. We say on line 1, it says save best only. It won't use the last model. It would actually go back and use the best model up to that point. So this is kind of a nice thing. And you can see when you actually start to do the training on line 5, we give it that callback, which means even though we've told it to train for maybe 200 epochs, it may actually stop early. It may stop after 50 epochs and say, look, we started to overfit, so we stopped. Okay. So that is it, and you use the H5. I like the JSON format better, but we were running into a problem with the H5 format. Here's an example, what we had done earlier. As you can see, instead of running to all 150 epochs, we end up stopping early around 50. And as you can see, it started to diverge. And again, to be clear, it won't use the model at that 50th epoch. It's probably going to go back and use the model somewhere around epoch, maybe 20 or 25. Okay. That's it. That's all for that part. And we will actually jump into some code. And maybe I could take questions now, but some of what I've discussed, we will actually run in the code, but certainly happy to take any questions right now.
I think there were some questions, but James and Ify, I think, replied to most of them. Have we missed any? Maybe more clarification on how the compiling and fitting and prediction. So we have 3 things that work. So compiling is mainly to build the model, which is specifying what are the layers, what are the parameters. And then in fitting the model is when you give it this architecture, which you specified in compile and gave it to fit when you train the model on this data using this architecture. And predict is actually when you use the test data for predicting how is the accuracy for on the test data. So when you are working on the data, you split it in train, the one that you use for training the model, and validation and test. So the validation is very important in deep neural network domain, because this is when you are trying to optimize the parameters. And I think there was some of the questions here about how to split that and why we need that, because this is mainly when the fun happens with this kind of knowing whether that's overfitting or underfitting and fine-tuning the parameters. So validation is very important for this stage to make sure that you are going through this rightly. The other thing is for epochs. What are the epochs and what they are doing? So the epochs is one run through the whole training data. So this is using this architecture on your data. One run across all of that is one epoch. If you have more epochs, so you have more iterations in the mechanism that James has explained. And this is the more epochs you have, the more iterations you have on the whole training data. And then you might, that's why when it comes to a point that you see the overfitting, because you have went through this many times. So when it sees the test data, it's very overfitting on the training data, then it doesn't do well at the end. Or you don't need to run all of this. I think someone has a question. Is that James?
Yeah, thanks, Sarah. There's another question in the chat that might be worth clarifying. In some of James's earlier code, when we did the test train split, I think we used the notation Y and X, and I think it would be good to clarify why we use that notation and kind of what it means.
Yeah, no, agreed. And I see it in there as well. And there's an additional part to that question. So the normally it's X is we normally think about it as a function, right? So normally we, I guess, traditionally have thought of the input to the function as X, and the output, what it produces, as Y. And linear regression is really then trying to take the X multiplied by weights that basically will predict Y, and part of that is the optimization part where we reduce that loss function to learn the weights. So in any case, that's why we traditionally still use X and Y. And then we did a little bit of extra stuff in our code where we took the X, and it's X is a vector. So to be clear, X is normally not just one number, it's actually a bunch of numbers. So that's what we did and we did something a little extra as well. We then took the input data, X, which is, I think the way to think of this is that it's a bunch of rows. It's just an Excel spreadsheet, if you will, a CSV file, and that you have columns and rows. We call the rows instances, and we call the columns the features. And again, this is very similar to linear regression. That's the way I think you should think about X, and then Y, again, is what you're trying to predict. We then split that into a training and test part. And the training part is used to do the optimization. And then the test part is used to do the evaluation of the model. Hopefully that's clear. I wanted to answer the second part of your question, which I think is quite interesting, which is what do we want? We want to find the optimal weight. Does that mean deep learning method can ignore this limitation about the no? Really, if you use like the architectures we use and it was a simple linear regression problem, it is doing the same thing. It's trying to find the optimal weight that will optimize the linear model. Now, with linear regression, there's only one answer. That there's only one, how can one say, set of weights that optimizes the weight, so to reduce the loss function. When you actually get into more difficult problems, to include the one we'll look at today, it turns out there may not be an optimal. There may be many local optimal. So again, with the linear regression, it's basically what you're trying to learn, minimize the loss function. It can be shown that there's only one minimum, and we can use a deep learning model. We'll find the same minimum that linear regression finds. So the difference is that the deep learning frameworks that we're learning can do much more than that. They can actually find, if you will, a set of weights that actually minimize that loss function. When you have you may have many minimums, so to speak. It's a little, it's a little troubling that we would love to say that there's only one optimal answer, but we can't guarantee that. It turns out we can only in the simple case of linear regression is that the case. When we look at more difficult problems, it turns out that there may be many minimums, and the learning frameworks, deep learning frameworks, we'll find one of them. I'd say hopefully they find one of the how can one say, minimum ones, but in any case they'll find a local minimum. I'll put it that way. So hopefully that wasn't too muddy. And James, Thomas, or anybody else certainly add to that if you like. And Quinga, hopefully that answers your question.
Yes, it does. Thanks, James.
And I think I'll turn it over to you, Effie. And Effie, on the code, I think on the regression, so we could probably go to where we do the TensorFlow, where we do the image, and maybe we'll stop there and jump to do the skin cancer images.
Okay. So let me share my screen again. Okay, so I've jumped here when we start using TensorFlow in this notebook. Before that is basically some of the information that James has already said on the slides. It's some more input to have on the notebook just in case it helps. But if you go ahead and scroll down towards TensorFlow 2, so we can run some of this. Sorry, James, you said to jump to the image. Exactly.
Oh no, you can run through those, I think, but then stop at the MNIST, the fashion MNIST image.
Yeah. Okay, cool. Okay, so here we have again the section where we import the libraries. You can see here that we're using TensorFlow. Just to say, you might have gotten a message from Colab that you haven't been active and you might need to restart the session, but it should have an option there for you to do that for the runtime, essentially. And then this is the code where you compile the model and train it. So when you click on that, you should be seeing the training and the output. So that might take, okay. So we have the classification, again, between, you know, is this an iris or not, iris setosa. And with, if you can see from the image, there is something different from what we saw earlier. So this is the discussion point here. How is this different from the previous results? Can anyone?
So as you see from what James mentioned before, I think in the slides they were showing two different images about the different initialization. So when you run it, you might see a very different image from what if he's showing in high screen, because of the initialization, it starts randomly. So it depends on where it starts.
Yes, very good point. You might not be seeing exactly the same image. Yes, James.
Why doesn't it seem to kind of fit as well as the original scikit-learn kind of single perceptron? It was like the lines aren't diagonal in this one; they're kind of horizontal. Yeah,
no, I agree. I think that I can answer that one, Effie. I think it doesn't fit as well. I think that I think something like an SVM, a support vector machine, would do a little better with this problem because it would find that maximal marginal classifier, so to speak. It would stick probably a line more so in the middle. So with this example, you know, with the, how can one say, as it's finding this boundary, I think to make this better for this, using this kind of a TensorFlow approach, you will want to get more data. You will certainly want more data near the boundary, so it could actually learn the boundary. So right now, the two clusters, this boundary is just as good. It does actually a pretty good job on the accuracy. It's just that we would like, you know, as humans, we look at that and we say, okay, I think this boundary would be better. So, you know, as far as it's concerned, this boundary is just as good because as far as the loss function goes, this is still a very minimal loss function. So I think to get this one to be better, you will want to get some more data. And this is a little outside the context of this session, but some data is more informative than other data. So I would, you know, I think to get the TensorFlow to be a little more stable, to find a similar boundary, you want to get more data, and you probably want to get more data that's a little closer to the boundary. So to answer your question, it just doesn't do as well, James. It's just, at least with the small amount of data that's like this, we end up getting, you know, we get a different boundary each time. Sometimes it's okay, it seems good, but sometimes it's, at least for us, it doesn't seem to be as optimal.
Cool, thank you.
Okay, so if we scroll a bit further, we can see the simple regression example using TensorFlow. So if you go ahead and run this, and here we're again compiling the model using this loss function and this optimizer, and then it's training. And you can see here, did it run already? Wow, that was fast. So you can see all the epochs here, 500 epochs run. And based on this output, what do you think about the accuracy? And is the number of this epochs that we used, is this appropriate for this problem? So what can you tell from the output that we're getting once we run and train this model? Open for discussion.
And maybe to add one extra thing to that, Effie, I think the very last line is the prediction on the input of 10.
Yes.
And if everybody recalls, we expected that to be 19. It's not 19, but it's pretty close. But so that's certainly, again, just to explain a little bit of what was that very last line.
Yeah, that is this line here. Yeah.
And I guess part of, go ahead, Sarah.
Go ahead, James. No, I was just saying that if anyone wants to comment on the number of epochs, that's it. Go ahead.
I was just going to point out, is it the case that it's always that loss function is always going down? I'm looking at it on every epoch, and it looks like it starts fairly large, relatively large, and then it does seem to be getting smaller. Is that the way to interpret that? So maybe a question from me.
Yes, that is the case. And keep scrolling up. And yeah, it starts from 0.6, essentially, in the first epoch. And then if you scroll all the way down, it ends up being really, really small. So yeah.
Yeah, when I change it in the runtime, the epochs to 50, for example, for the one predicted, for the one label to predict here, for the one number, it should be 20, right?
Or 19, I think.
19. Okay, so the one that I got here is 17.14. So that affected definitely the accuracy with less epochs.
I like it. So Laura ran and got 18.9999. So
that's
ran
pretty
with
accurate, I'd say.
yeah, somebody ran it with Betsy ran it with maybe only 50 epochs and got 16. That's definitely want to run with more epochs. Let's see. Yes, absolutely. So very good what James said. We're doing all of this right now. If you actually go in and look, we just kept training and training and training on the test set. We never actually talked about not test set, excuse me. We did all of this with one set of data, if you will, the training set of data. We didn't talk about a test set with this. So there's also a good chance that this model is overfitting. So certainly some things to keep in mind here. But definitely, certainly some nice comments. Also, Ricardo had a comment, why did we choose the stochastic gradient descent optimizer? Most of them are all based on the same idea that as I was mentioning earlier, with linear regression, there's one minimum. The loss function is basically taking a step trying to find that one minimum. So you keep taking really small steps trying to find that one minimum. Now, when we actually look at more complicated problems, you can imagine like a golf course. So if you know what a golf course, and you can think about the layout, there are lots of little valleys and things and hills. And you can imagine just dropping onto that golf course somewhere randomly. And then you want to try to find the minimum point. So you take a little step and you keep doing that. So that's the overall algorithm of what's happening here. There are lots of variants to it. So all of them are up under this umbrella of stochastic gradient descent. Adam, for example, will be changing how big the steps are and automatically changing, maybe making the steps smaller, etc. So there are lots of different variants of it, but they all fall into that And it turns out for many problems, there's no closed form solution. There's no easy, you can't just take the inverse of a matrix and compute the solution. So stochastic gradient descent turns out to be a very, has been determined really through empirically to be a nice empirical way of finding a good set of weights to minimize the loss function. And there are lots of variants. Again, when in doubt, use ADAM, A-D-A-M. It's again, very much just an optimized version of stochastic gradient descent. So Ricardo, hopefully that answers your question. And sorry for the long-winded answer. Okay, and what was the next one? Was it the fashion MNIST? Hopefully it is. Yes, perfect.
Yes. So you'd like me to stop here so we can move to the
Oh, we can go ahead and run that. Yeah, we can go ahead and run this one real quick, and that'll be a good segue into it.
Okay. So yes, here we're using the fashion MNIST dataset, which is publicly available so that we can work with images. So if you go ahead and run, so you can see this line here is loading the data. And you can see in the output here, downloading the data and starting the training. We're training for 10 epochs here. And you can also see how the loss and accuracy change while it's training each epoch. A bit more time to see the output now. The other one ran so fast.
It was only 6 examples in the previous one, so fair enough.
And this is the image that we're trying to predict, essentially. This kind of ankle boot here.
So maybe while we are waiting for the number of epochs to reach, so I think one of the questions for discussion, how many layers are in this one? So anyone wants to comment on the number of layers, or there are some thoughts? And we got some results.
Yes. So we have the plot of loss and accuracy. So red is the training, blue is the validation. And we can see that they are converging quite nicely. And here you can see the results. In the bottom, you have the summary of the model that is trained. And before that, you can see what the prediction is. So the first thing is an ankle boot, which is indeed what the initial image was. So the prediction works quite well. And the next ones are other outputs that have lower kind of scores in the prediction. So yes, maybe some of you, any of you can answer some of these questions. Oh, we have things in the chat.
Yeah, we do. And I think James answered one that, yeah, you can definitely get in. I won't say a false minimum. You can get into a local minimum. This absolutely happens. So a lot of research continues into trying to come up with optimizers that try to avoid this, as James Thomas had mentioned. Does the accuracy and loss essentially represent the same thing? Ideally, yes. It's not always the case, but generally as the loss goes down, the accuracy goes up. That is true to Harry. That's correct. And sometimes when I teach, I do have to make sure that I have to remind myself that we're minimizing the loss, not the accurate. We're not maximizing the accuracy, but we believe that there's a connection between them, that by minimizing the loss, that increases the accuracy. And then Ricardo, can we use this notebook to make other tests later on? And James Thomas, absolutely, yes. We encourage you to do that. Please do so.
Yes. So basically, if you go file, you can save a copy of this notebook either locally on your computers or in your own GitHub repositories. And you can, again, you will still have access to the GitHub repository where the notebooks are. So you, even if you don't download them now, you can download them later and use it however you want. The presentations that we use are already there. Maybe I can just go ahead and also show you what is in the GitHub repository. So in this folder, we have the data files that we will use right now for the skin cancer example. In this folder are the 2 notebooks that we've been using. Here you can find the PowerPoints. And in this folder, in the references, there are some papers that are relevant that you could look through if you want. And yeah, some instructions here that we have already done and what you can find in the folder. So yes, this repository is public, so you can always access it if you want. And on that note, should I stop sharing so that we move on? Okay, yes.
Okay, and we'll finish up the last part, which is what many showed up for today, which is actually we're going to take what Effie just showed where we had done. So hopefully everybody can see my screen full screen. Excellent. And that image where we flattened it, that's not ideal. We want to do better than that. And so this is where CNNs come in. Skipping through some of the caution on here, I'm going to go through this. So how can we, instead of just taking a vector in of numbers, so to speak, how can we take an image in? We kind of have an image on the left as input, and we want to have these kind of neural networks, you know, the same things we had seen to make some classification task. And what does this look like? What kind of model would do this, or what architecture would do this? I'll cut to the chase. The answer is convolutional neural network, CNN layers. So convolutional layers. So what they do is they basically will run a kernel, I guess really taking a bit of a step back. This just goes through some naive approaches. What we just did was a naive approach. A more sophisticated approach is really to use these convolutional layers, but they're really built on kernels, filters, as we would say, that really what these do is you could take this kernel represented here in this little yellow box, and we can run it over the image, and then it will produce an image as the output. It will basically, and you say, well, what use is that? Well, what these kernels do is they usually find something interesting in the image, such as an edge. So typical like an edge detector, and you can see the weights in this little yellow box in the middle here. There are weights in there that people have learned over decades that these weights from the left, this -1, -1, -1, zeros and +1s, that'll learn a horizontal edge, or so vertical edge. There we go. That'll learn vertical edges. So the image, the output image will basically be similar to the input image, but it will definitely have those edges, those vertical edges highlighted or accentuated. And you may say, well, that's great, because that's good, because a lot of times when a human, we're looking at an image, we're looking at the edges to try to figure out what's in it. But then the problem becomes, well, how many different types of kernels could we have? Well, the answer is they're an infinite number. So instead of learning just kind of weights as we had seen before within the perceptron, what we actually want to learn now are the weights in those kernels. So hopefully I'll wait. I may have stuck there for a little bit, but so now that's really what's happening now is we want to learn a bunch of kernels, and we want to learn the weights in those kernels. Okay, so we don't, to be clear, this one is showing where we're learning just one kernel. What we want to do is to learn multiple kernels, maybe many of them. So this one, we might want to find the vertical edges and the horizontal edges. We might want to find other types of edges. And so we may have many of these kernels, so to speak, or filters, I should say. They're used interchangeably. I'll try to continue to use filters and the weights in those filters. And that's what we want to learn. And that's what you're learning in a convolutional layer. And as you can see, if I have 2 filters, I have kind of 2 images as the output. If I have 3 filters, I have 3 images as the output, so to speak. And those, again, this will sometimes be called channels. So again, just running the skim, we have the convolutional layer here, conv2D layer, basically with 4 filters. So we take the original image in, and you can see we get kind of 4 images or channels as output. And so, which is interesting, the width and the height stayed the same, but it actually in some sense got deeper. And so at a high level, this is what happened. The image, something on the left, the input comes in, and we have this kind of volume output on the right now. So this is what the function is doing now. And again, within the com2D layer are those weights on those filters that we want to learn. So again, it's not unusual that the input will be, you know, width and a height and some depth, and the output might be the same width and height, but usually it could be less. But typically also the depth usually gets larger. And sometimes we call those feature maps. But the point of all of this is to say we're finally getting to where we want to be today, which is, well, if I can have one convolutional 2D layer, what happens when I combine multiple? What happens when I put lots of these in a row with images? And the answer is typically what happens, and has been shown for certain types of images, that the low-level features will learn very basic features like lines, things like that. The mid-level might learn eyes. For example, if this is a facial recognition task, the middle-level layers will learn what an eye is. And then the high-level features will take that as input. And then we know that a face should be 2 eyes, nose, mouth, you know, etc. And so the high level, that's what the later features will learn, or the high level later layers will learn those features. And this is really a nice interpretation and has been shown. It's very hard to understand this because it's very difficult, and it's really not known when you get multiple layers what features are being learned. And this is what makes these very difficult to interpret. But certainly with some things like facial recognition, this is actually what's happening with those multiple layers. I will skip these two just because not important for us, but this slide is important. This is when we actually take these multiple layers and combine them in this way. This is what we call deep learning. This is what the term deep learning comes from. We have deep layers, okay? The early layers learn basic features. The later layers into the architecture learn high-level features. And as you can see, in this case, we're taking the image, and the width and the height are getting smaller, and we're getting more and more feature maps. The channel is getting deeper. And then we eventually take that, get those numbers, so to speak, and then make a prediction. The top layer is going to make a prediction on the classification. Okay, so that's what we're going to do. Pooling layers basically will reduce the size of the image, the width and the height. They don't increase as you can see, the input and the output, or the channels. The depth is the same, but it changes the width and the height. That's typically how we do that. And over time, people have learned that typically having 2 convolutional layers followed by a pooling layer is a good architecture. That's very much empirical, but kind of hyperparameter tuning. So that's what a pooling layer does. So in any case, just to give you a simple CNN example, here's the architecture on the bottom now. We have the input image. It has 3 colors, red, green, and blue layers. That's what the 3 stands for on the left. 224 by 224 images. We go through a series of convolutional and pooling layers. Eventually, as you can see at the last layer, the volume is a 28 by 28, but it's got 64 kind of feature maps. We then flatten that and then make a prediction. And so let's see, anything else? So we have, let's see, activation functions. Let's see, look at another example, see if I can find one. Okay, so in any case, that's that one. I think there might be a slight bug on that one. I think the last one, oh no, it's there, excuse me, no bug. Line 11, you can see we add that last dense layer and we add the number of classes. So one thing I might do on that one is if it is a classification problem, we would, let's see, we don't show it here, but you'll see that we actually use I believe that should be a softmax there on that last one. Apologies. I think there might be a little bug on that. We'll see the code in a moment. So nevertheless, the point is that architecture that you see there, you have the convolutional layer, max pooling, convolutional, max pooling. So hopefully you can match up what you're seeing in lines 3 to lines roughly 11 and see that that's the following the architecture down below. So I do think that I think it's actually much better, so to speak, to think about the architecture first and then go develop the code. but you should absolutely be able to go between the two. Okay. Finally, skin cancer. We took these images from Kaggle. They did not come in the best format for TensorFlow. TensorFlow likes all the classes of an image to be in the same folder, and the folder name becomes the class that you're trying to predict. As you can see here, there are 7 folders, so there's 7 classes we want to try to predict. I don't know all of them. I do know that the MEL is melanoma. That's cancerous. That's not good. And I think the BCC is also cancerous. I am not an oncologist or a dermatologist, but some of these are definitely problematic. You might even imagine changing this problem to be binary classification, so cancerous, not cancerous. What we're going to do is we're going to have it still try to predict which type of mole it is of the 7 types. So we've already rearranged this code. This came from a Harvard study, and there was a cancer research institute involved. So they collected this data. I want to note they collected the image data. You'll see we also have the gender, the location, and the age of the person. We're not going to take that into account in this session, but I think including those things could certainly be an addition. Maybe that wide and deep architecture we talked about earlier would be a nice addition to basically increase the accuracy of it. So this basically will get the training set. And you can see, I should say very quickly, some of these images are, if you're squeamish, some of them are not nice to look at. So just be forewarned that if you are a little squeamish, that some of them are pretty rough to look at. And so this is the example. And I think if you look behind that one, you'll see I did the activation function as a softmax. So in any case, with this fairly simple example, I created a test set and a training set, or if you will, a validation set, and I get about 50% accuracy on this. And this was with the small data set. To go back to here, there are 10,000 instant images. This was too much to put into GitHub, so we have 2 reduced versions of this. We have one called small, and I can't remember, maybe it's 1,000 or 2,000 images. And then we have one called tiny that might be 500 images. Those are definitely in GitHub. And so in any case, we're going to use small. And in fact, this one was with the small set. And you might be wondering, well, that's not great. How can we do better? And maybe we could take another model that somebody had trained and maybe take the features that had learned, the low-level features that had learned, and maybe do better. So I'll explain this in a moment. What I'm talking about here is that we would like to do better in this, and with the small amount of data, we didn't do that well. We'd like to do better. So a couple of other architectures to consider are residual nets. I won't go into detail on this, just to say that there's this kind of skip connection. Again, you can use the functional API to do this, and residual nets have actually worked pretty well for certain types of problems. And so this is creating our own residual net. Basically, the previous slide, that architecture there, and that code mirrors that architecture. And now, instead of using convolutional layers, we'll use ResNet, residual layers. And so you can see that one there. And again, this architecture has turned out to work well for some problems on ImageNet and other things. And so you can run that one. There are variants of it with 34. That's the code to create 34 layers. ResNet 50, 105, 152. One of them won a competition. I can't remember which one on ImageNet. So to say that we can get a lot of layers is an understatement. I will not pretend to say I know what's happening in all those layers. This is where the interpretation gets really difficult. But this turned out to be a successful one. So I tried the ResNet, and as you can see, it did better than that simple architecture we had before. It gets to about 60%. Still not groundbreaking. And when I'm saying 60%, we're getting to 60% accuracy on the validation of the test set. That's the one that counts. So how can we do better? Well, maybe we could take a model that's been trained on a previous data set, not necessarily skin cancer images, but that have been trained on images. And maybe those low-level features are useful for us also. Maybe it learned those early layers, those features that it learned, maybe they're useful for our problem also. We don't know that. There's, in some sense, some intuition you would have to have about this, you as the modeler. And so in this case, what you could do is we could take something like ImageNet, which might be trained on flowers or other types of classes. and it basically learned these low-level, mid-level, high-level features, and then they had the top-level task, layer 4 in this case, or layer 4 was kind of right before the top layer. And maybe we could copy all of those. You know, maybe we could take a layer 1, 2, 3, and 4, copy those weights that it learned to our set, on the bottom here, which is the skin cancer images. And maybe if we start there with those weights instead of initial, random weights, maybe we can do better. Conversely, maybe we can just copy the low and middle level features. I don't know what that is. It's just those earlier layer features. Again, if you have 150 layers, I can't tell you which are low level features or mid level or high level. Again, something you as a modeler have to go through, but it's very common to maybe take some of the lower layers, take those. Then you can actually, if you will, freeze them, keep those weights, or you can actually change all the weights. So many different variants here. And in some sense, I don't want to go into too much detail on this because I think I want to get to code. The point here is that it's very common that you will copy over the lower layers. You might freeze them so they don't change during training. What we're going to do in the session is we're not going to freeze them. We're going to unfreeze everything and train it on our new data to see if that helps us. And it turns out, very surprising, the short answer is it actually does for small data sets. We found when we got the larger data set, it didn't help as much, the transfer learning, okay? So there's some stuff on the transfer learning. I won't go through all the, read this to you. I will only say the one thing at the bottom, it's not guaranteed. Just because you take a previously trained model on images doesn't mean it's going to help your problem, okay? There's no guarantee that this will actually work. It was surprising that it worked in our case. Each problem is different, and so it certainly may not work out. There's another module architecture called an inception module. It basically looks at kernel, they're looking at different size kernels at each layer. Won't go into detail on it, just to say that it's already provided for you. And so it turns out they've already trained, TensorFlow has already trained these different types of models, ResNet, residual networks, and these inception modules on ImageNet. ImageNet has 1,000 classes, 2.5 million images. So you can take what they've learned, you can basically copy their weights to your model. So what's happening here, actually jumping down here, is exactly that. So on line 2, we basically take the exception model that was trained on ImageNet, and we say, give me that model, give me all those layers and all the weights. And then we go through, on line 5, we kind of create our own classification, or our own architecture, so to speak, as an output layer, where we want to predict 7 classes, not 1,000 classes. And then we basically go through and copy over. You'll see on line 6, we're creating a new model, which takes the weights from the ImageNet model, the base model, and we actually then combine that with our model, or if you see our layer, the output layer 5. We go through, by default, all those layers are set to be, I believe, trainable faults. We go through and make sure they're all trainable. Like I said, we don't freeze any of them. Freezing means to make it so that the weights don't change during training. So we unfreeze. In other words, we make trainable equal to true for all of them. And then we continue with the code. And so now on line 13 and 15, we're actually training it on our data, but we're starting with the weights from the exception module. So that's an example of transfer learning. And so how does this do? Remember, we got 60% before with no transfer learning, or roughly 50% with our simple model. Now, if we actually start with ResNet 50, we actually get up above 60%. So that helped a little bit. If we try another one, MobileNet, we get up to 65%. And now we're really making progress. With MobileNet V2, we actually approach 80% by using this transfer learning approach. EfficientNet does well also. It doesn't always work. Here's an example. It does, like I said, it's not guaranteed. And the exception one, I think for our case, turned out to be the best for transfer learning. Again, we have a small amount of data, and the fact of using it. And by the way, even if the small amount of data, we don't expect it, in this case, the accuracy turned out to be better. Sometimes it's just the fact that you can get a better model quicker. You don't have to go as many epochs. So there's really 2 potential advantages of transfer learning. And I do want to emphasize again, it's not guaranteed. So in any case, that's it. And I will end with that and let Effie go run some code. I've covered a lot. I would like to answer some questions, but I think it might be better to jump into code just to make sure we don't run out of time.
Yes, let me share my screen again.
Did I stop sharing?
I think I can. It's without. I think I'm sharing now. So now we need to open part 2. So if we go again, file, open notebook, and again, we will need to also copy paste GitHub repository URL here. So you will need to open part 2. Yes, changes will not be saved in the previous one, but we don't care. At the moment, we don't care. You can save it if you want. First of all, we need to load the data set. So the first line is basically getting that data set from GitHub. So as we said, we have 2 data sets on there. One is called small and another one is called tiny. So there are 2 lines here. The first one gets one and the other one gets the other one. We recommend using the tiny one if you have not been allocated a GPU by Colab. So anyway, too many sessions. Okay, you have to stop the previous session. So you need to end this, terminate, and that should probably work now. And you might need to also check that you are getting a GPU from the runtime settings. So this, if you run this, you should have the data in your Colab folder. So you can check that if you click on this icon here, files, you should have this zip file in your folder, depending on which data you downloaded. So either health small or the health tiny, it should appear here after you run the wget command, either this one or the next one. So after we do that, you need to unzip the file. You will need to rename this line if you downloaded the tiny one, just to avoid any errors. So once you unzip, the folder should be visible here on the data again. And you will be able to see the classes that James was talking about, the subfolders. And once you have done that, I will maybe wait a minute to check that you already all have at least some data to work with. We have something in the chat.
There was just a question as it's running. Effie, is it possible to generate images from each layer to see the features the layer's picking up? Yes, people have done that. There's some nice visualization. There's a nice library out there. I forgot which one it is to be able to do that. But having said that, sometimes it's not it's not human interpretable. So, but
yeah, that's the thing with deep learning. You don't really know what it does. It's kind of a black box. Can we get some thumbs up if you have data in your Colab session? Okay, that's good. Okay, so after that, we need to import some libraries. So if you run all these sections, you check what version of TensorFlow you're using. So for me, it's 2.12. Import some plotting libraries. And here you can check if you're using a GPU. No, here you can check if you're using a GPU. So we can see that it's off. Okay, so I'm not using a GPU. Yay.
Let's see. I thought
I was
using a
allocated one.
Oh, it may just be a parameter of it. It looks like you're using a T4, you're not? No.
Yeah, I have a GPU, so it
Yeah,
looks
yeah.
like I have one. Okay. So yes, this is where you can check, guys. If you see click view resources, you should be able to see what resources you've been allocated here. And you can see that if you want more, you can upgrade by paying. Okay. So here, yes, you can check how much RAM you have allocated, importing some more libraries. And once we get to that point, we are ready to start creating our custom CNN model. So these are some parameters, the batch size that we're going to be using, the parameters of the images, the number of epochs. And here is where we create the training data set to be used by TensorFlow. So make sure here that you're using the correct name of the folder. So if you downloaded the tiny data set and your folder is named health tiny, you need to rename this so that it works. So this one here creates the training data set in the formats that TensorFlow uses. And you can see that you can define the split of training and validation, but you need to create the validation data set separately in a separate command, again, by defining the split. Here you can get the class names from the folders, as James said before. Sorry about the images, guys, but this is some images from the data set that we will try to classify. And we're getting to the good part. This is where we define the layers of our model. This is a custom model that James has created.
And it does have it on there. You can see the softmax is in that last layer. So I did have a bug in the slides there. So yep.
Yep. So here we are defining the optimizer. So here we're using the Adam optimizer, different from previous one. And we can see all the parameters. And it's time to train. So we're running a model fit based on the training data set, the validation data set, and the number of epochs. And we'll see how long this will take. Might take a few minutes. But okay, I will go back to the table of contents. And while it is running, we have 30 epochs. Maybe we can look at the discussion points so that whilst you can see the output, maybe you have some observations to make. It's quite fast. We have some.
And how much slower is it when you do it with a CPU?
I think it was, I ran it without a GPU, yes. So this is quite fast now. I think it took this part, the custom model, took me maybe 3 minutes to run without a GPU. So the training is done. You can see here loss and accuracy, that's the training ones, and then validation, loss and accuracy here. And we can also plot it to see. So you can see how the accuracy increases as it trains. And we have, what is our accuracy at the end? How well did our model train?
So I think the question that you ask yourself when you see this graph is that more epochs will make things better. And this is something that if you can see a plateau somewhere that there is no change, so that means if you added more, it won't make much change. But in this case, do you think is that the more epochs is the problem, or maybe more data, or maybe the architecture? So I think this is things that you need to think about when you see this kind of graph. And also just bear in mind, this is a classification for 7 classes. So 0.4, it's not good, it's not great, but it's better than random. So it's not terrible as well.
Yes. In this kind of things, yes, you get a result. And if it's not what you were expecting, what do you do? How do you think about improving it? Do you give up and say this problem is unsolvable? No. You try to change some things, maybe reconfigure how much data you have, or yeah, as Lara said, you can train it for more epochs, see if the accuracy improves or not. And then if not anyone has any questions or observation, we can move on to the residual CNN.
Can we jump into the transfer learning one?
Yeah, probably, because we are running a bit out of time. So I will just scroll down to transfer learning. Hopefully we don't need anything from the previous one. I don't think so. Yeah. So first of all, we need to get our base model, what we need to transfer from. So here we're getting the exception model. So you download it from the API that already exists. And we, as James said, we are unfreezing all the layers here. So all of the layers are trainable. And these are the parameters of our model. We define the number of epochs to be 20 here, and we are using, we are training the model now based on the exception model and ours. The point of this is to see if our accuracy will be improved based on what the result we had before.
Is your GPU still working? It's dead.
I don't know. I don't know. Yeah, it's working.
Yeah.
Full on.
So maybe we'll jump to the results. Yeah, it's not running. Yeah.
Yeah.
In fact, that's one. This model has quite a many more parameters to learn. I think it tells you above, right, Effie? How many parameters is it learning in this one?
Yeah.
Oh, almost 21 million.
Yeah, it's a lot more. So that might have been faster if we had frozen some of the layers, for example. But now we're retraining everything.
And is the previous result down at the bottom at the previous run?
Yeah, I think so. So here you can see the accuracy is this line for the training and the blue one for the validation. So what do we observe? That the accuracy has indeed improved using transfer learning. So this is from when I had run it before. The results are still visible because this is epoch number 3. And again, we can save the model, as James said. you can use this command to save and then use it later to restore it using this load model command, and then it retrain. So you might have saved a model when you trained it up until a point, and then you want to continue from there. So there is this option that you can do. And yeah, I think that is about it. The only thing that we haven't shown here on the code is the residual CNN, but you can go ahead and run it and check the results. Okay, sometimes it goes a bit faster, sometimes it goes slow, but yeah. It takes a bit of time to train a model.
Yeah, and I think, I don't know, the original ImageNet training, would have been months actually when they trained it.
Yeah, I think so.
So there's a question, why would you freeze certain layers over others? Would it be conducted via trial and error approach? Sadly, yes, but there is a little bit of reason to it. You generally freeze the early layers. You might imagine starting with all the layers frozen, and then you start to unfreeze the top layers, going down to the lower level features. You wouldn't do it the other way. Generally, what you want to do is keep the low level features that were learned as they were. So it's normally the later layers that you might unfreeze. So hopefully that makes sense, that there is a little rhyme or reason to it, that you unfreeze the layers that are deeper into the network, and you would have them contiguous. You basically have a contiguous block of layers that are frozen, and then a contiguous layer blocks that are unfrozen. Where that line is between the two, that is by trial and error.
And again, here you can see for each epoch, the training loss and accuracy decreasing and increasing respectively. And the accuracy is always really good in the training, but that's why the validation is really important, because that's where you see actually how well it performs, because you can see the difference. The training is almost 96%, while the validation is 70, and it started from 16. So that's where you can judge how well it's training, or if it is training. So for example, if you can see how long it takes, if you started training something and you see that the validation accuracy does not change that much, it's time to stop it. There's no reason for you to just keep going and then adjust some things to see. So that this is a way to check how well it's training while it's training, and not waste too much time. Just a trick.
It's also good to note that the big jump between epoch 2 and 3 in the validation set. So
yeah,
the jump wasn't that high in training, but was high in validation. It went a little bit down again, but it was actually in the 60s for some time, and around 60 and 70. So I think it's and the way that transfer learning where it started was 0.56 in the training accuracy, which is good, a good starting point, and then optimizing into that until reaching 96 for, I think it will reach, I still have mine running as well, but it will reach good accuracy at the end. So but where it started because of transfer learning is way better than when it started from scratch when we had our custom model. And this is the whole point of transfer learning, is to start somewhere. Yes, thanks, Effie. Okay.
Yeah.
So we had this as a start, so we have 20% more at the beginning because of transfer learning.
Yeah.
And then I think Matt had a question, does saving the model also save the trained weights? The short answer is yes. In fact, I think to me, saving the model is saving the weights. The model are the weights, so to speak. So if you trained for 20 epochs and then saved the model and reloaded it and trained for another 20 epochs, you would have trained for 40 epochs. That's exactly right. I think if you scroll down, Effie, that's what you did. You loaded the model and started training again. If you keep scrolling down, you see that that basically read a saved model and then did the fit again for another 20 epochs or so. If you scroll down, you'll see that it actually started at a very good place where it stopped from the last time. If you look at the curve, actually, Effie, the plot, So you can see that's a loaded model. So it almost like it picked up where it left off from. So to answer Matt's question, absolutely. It's very similar that if you train for 20 epochs and save the model, then reload it and train for 20 epochs again, that's pretty much the same as just saving or training for 40 epochs.
But now you have to be careful with the overfitting.
Absolutely. We haven't, we kind of sidestepped that a little bit here, but absolutely. And I do want to leave with another thing, some other observations that we haven't discussed that are not in the or in the thought, the plots, the code. If you try with the full data set, transfer learning does not work as well. It turns out that if you actually take the full data set and use that architecture that that we started with from scratch, we get close to about 80%. It takes a while. It does take a lot of training, but we actually do get close. And the transfer learning really doesn't help, other than the fact that maybe we could have gotten by with fewer epochs. So at least in that sense, transfer learning might also, it didn't increase our accuracy, but it could have actually helped us reduce some computation. The other thing that we didn't do in this was to take advantage of those other features. We're only using the image for this, but certainly where it is, you know, the people, when you, if you know this, that a lot of times the heads, which usually gets most of the sun, or the arms, this is usually where skin cancer happens more. So including this type of information in the model, we didn't do that, and doing these other types of things and creating a model that takes these other features into account, I think would help increase the accuracy, and always getting more data will help.
Yeah, so I think when you guys have time, I think it will be useful to download the whole set of data and try to run this same kind of architecture on larger set. I think that the idea here is to think about what can be changed to make this better or more accurate. So is it more data or more features like what Jens just said, or the architecture need to be changed, how to tune transfer learning in a way to make it more efficient. So I think this is all still kind of things that we couldn't cover in the 2 hours, but I think that's kind of things that you can explore beyond this session.
Yeah, absolutely. So very good. And I think Fadi has a question. Can we start from an epoch with the max validation accuracy? Yes, you can do that. I think if you do that callback thing that we had shown in part 1, it saves the model that has the, I say the best. Oh, I'm sorry. Yeah, the max value accuracy. Yes, I think if you go in and look at that, you can tell it to actually use that as the metric that it uses, and that it could save the max value. I haven't done it, but I think it can be done, to answer Fadi's question. That I think you can do that.
Few more epochs to go, right? Almost there.
And you can already see how the validation accuracy has increased even more now. So I think this might be better, the result. We'll see, but yeah, we'll see.
I do think when I went through this one, to let all the members know that, particularly with this model with 21 million parameters, using a CPU, it's not going to be the difference of 1 minute and 5 minutes. It's going to be the difference of, okay, we may wait 5 minutes here for this one. The difference with the CPU is probably going to be 10-15 hours. So this is why CPUs have become so important, and TPUs as well. In fact, we're using a TPU for this one, but basically specialized hardware, while having access to it, is very important. That using it, it's interesting. There are other problems where CPUs turn out to be a little better, but at least for image tasks like we're doing now, it turns out that these GPUs and TPUs increase it by 2 orders of magnitude. So thanks, Syed. So yeah, I know that we're coming to the end of it, or a little over. And I guess at this point, as we close, as it finishes up and gives us our last one, are there any final questions? I don't see any. So James Thomas, I don't know if you're still out there. So okay, there we go. You got your best one was not so bad, 78 maybe.
Yeah, around here. Yeah, kind of dropped a bit. It's fine.
We still need more epochs.
Yeah. Yeah.
But we don't have time for that.
But yes, thank you, Laura. And so, like I said, I don't know if James Thomas or is James Thomas still out there?
I am, yes.
Ah,
Thank you very
okay.
much to James, Effie, and Zara for such a great session and a deep dive into neural networks or CNNs for classification tasks in TensorFlow. So yeah, thank you very much. My colleague Will be posting the feedback form link again into the chat, so I can see lots of thanks coming up into the chat. As there's another question as well, which is from Matt. What do you class as a good accuracy, or does it depend on the question that you're trying to answer?
Yeah, I do think it depends on the question. With binary classification, maybe it's a little clearer. With 7 classes, it's perhaps not as clear. So yeah, I generally, I don't want to throw a number out because I think the answer does really depend on the problem. There are some really difficult problems where, 55% is a fantastic, result. So
Yeah. In this kind of cases, you just check literature and see what state-of-the-art accuracy exists and then try to improve on that. But yeah, it depends on the problem.
We have another question. Oh, sorry, go on, James.
Oh yeah, I did want to say one other thing. Also, if we changed it to binary classification, it would be, do you have cancer, skin cancer, or do you not have skin cancer? Then it's really going to depend on how you get it wrong. A false negative saying the person doesn't have skin cancer means it goes undetected. It's much worse error than saying you've got skin cancer, a false positive, and you don't have it. So that, so definitely the problem really matters. And again, like I said, if you, so accuracy, like I said, it becomes even a little more nuanced if you look at a binary classifier where the cost of a false positive or false negative is typically much worse than the cost of a false positive.
So we had another question in the chat, which was, is the video going to be made available for this session? And yes, the answer is it will be put on the Gene Golding Institute YouTube channel. There's also, I'm looking at my other screen, the schedule of events. That was another question that came in. Are there going to be similar events like this? And there are this week. So I'm just looking at the events now for Wednesday, Thursday, and Friday, and we'll post a link to this in the chat as well. If I scroll down, there's a number of in-person events at the university tomorrow in the Fry building. On Thursday, there are a number of in-person events at Bristol Beacon. And on the Friday, there's a number of in-person events at the Wills building at the university. But there's also online training events as well. They tend to be the ones in blue. So if I look at tomorrow afternoon, there's a session on applied data analysis in Python. Thursday afternoon, there's an introduction to data analysis in R session. And Thursday morning, there's an online session about graphical data apps. So that's using Python and Streamlit to produce an interactive data visualization app. And on Friday morning, there's an online training session for text and sentiment analysis in R. So hopefully, if you like this session, then some or more of those sessions will be interesting to you. So great, I can see lots more thank you messages coming up in the chat. So what I'll probably do now is stop the recording and then, yeah, just final message from me. Thank you very much to the presenters today, and thank you all for joining us.
Thanks so much, James, and thanks for the Gene Golding Institute for this opportunity to give this workshop. Thank you, guys.
Thank you, everyone. Yeah.
Absolutely.
Thanks all.
Cheers.
Bye.
Bye.